Hi everyone, thank you for being here. During this talk, we will be talking about defeating static signatures in black box antivirus engines. But first, let me say a few words about myself. I'm a security researcher working at the company that runs Insomnihack, and I have some background on antivirus software because I work on that since 2015. And I also happen to be the author of a project that we open sourced 2 years ago. If you want to know more about the work that we do on antivirus software, I can only recommend to you that you check out our blog. Here is the way my talk is organized. I'm going to directly show you a demo of the tool, without making any comments about it, but my hope is that I will raise the interest, keep you interested until the rest of the talk. And then I'm going to get some stuff out of the way, like why we do antivirus evasion research at LCRT. And next, I'm going to give you a quick refresh about the antivirus detection capabilities as I know it. And then we will be able to talk about the way we designed our tool. So about the demo, the demo gods are with me. It takes a bit of time to run until the end, so I will first run the demo and then I will continue to talk. I'm a man, so I can do two things at once. So here we have a component of a Meterpreter, and this is the tool that is the subject of this talk. I was sure it was gonna happen, but I have to quit the demo to. It's quite awkward to do that, but I've run the tool, and it's doing its magic. And while he's doing that, I can continue with the slide. So it will be open sourced on GitHub after the talk. It's 3,000 Python line of codes. And if it's that small, that's because we are standing on the shoulders of giants here, thanks to frameworks such as Ryzen, Leaf, and Keystone. And the demo I've just started is about Meterpreter because, I'm a pen tester and we like to use Meterpreters since many years. And we won't stop doing that. It works very well, but obviously it's detected by many antivirus engines. And the signature's name is Meterpreter, something API retrieval, which does not mean something to me. And the goal is to find the things that are detected by Windows Defenders or other antivirus engines. Let me switch to the demo. It's still doing stuff. And at this point, you don't have to understand anything. It will be clear by the end of it. It's actually done. And here, what I can already tell you is that if you patch the following bytes within the Meterpreter main component, you will be able to bypass Windows Defender. And at this point, I can't look at this binary data and make sense out of it, but it will be clear later on. That being said, I have to give you a few reasons because, doing antivirus evasion research might sound unethical at first, especially for a company like ours, because, we are a security company and we make the recommendation that you install antivirus software. If that were the case, why would we advise, would we try to bypass antivirus? The first reason I will give you It's based on a silly analogy, but it helps me get my point across. You know, you have this game where you're given a set of objectives and you have to take them out without making the guy complain. And I think it's almost the same when you are doing internal pen test engagements and you don't want to make the antivirus complain, either because you are doing a red team and you can't afford to be detected, otherwise it's game over, or during your internal pen test, you don't want to trigger the antivirus because it will make you lose time and maybe prevent you from exploiting vulnerabilities. The second one is the false sense of security. I've often met during several missions. You know, sometimes your person of contact is not very knowledgeable, and it's just about some new fancy antivirus, and the time is short, and the only thing standing between you and your domain admin rights are some dumb antivirus, and the tools that you are using for years now are detected by this tool. You would like to tell your client that it's okay and you will be able to bypass it if you have a few more hours, but at this point, they might not believe you and they will challenge your findings. It's one thing to scan for vulnerabilities, it's another to exploit them. And if you are not able to do that because of some security software, they might think that they are secure, which is obviously not the case. And a third reason is a funny one. There was a company that was selling a software and they were the victim of antivirus software because 39 different antivirus were detecting it as malware, whereas it was not. For us, it was obviously a false positive, but the company was actually worried that it might contain a virus, either because they were the victim of a supply chain attack or because some malicious employee did put malware in it. And the question for us is, how do you prove to your client that there is no malware in it? And how the client itself prove to their own clients that there is no malware in it? So we have to fix the false positive because Windows Defender and the other antivirus won't do it. That being said, let me give you a quick refreshment about the ways antivirus work that will help us make things in context later. So I have two distinctions here, before and after executions, because the tests that are realized before and after execution are obviously not the same. The first test that is done does not deserve any mention because it's file hashes. You change a byte and you bypass the antivirus. But they are aware of that, so they stack their detection mechanism on top of one another in the hope that they are more efficient with their detection. And the second test that is usually realized is static heuristic detections. It is most commonly known as artificial intelligence. And the third one is the subject of this talk. This is signatures, and we will know more about them later. And the last one is emulation. After your binary executed, it's not over. You can still be detected and killed. And that happens because the antivirus has several subscriptions about several events that can happen. And there is plenty of literature on the subject. Luckily for us, the antivirus have a pipeline of detections, and we can also have a pipeline of antivirus. So for the hashes, you just change it a bit. And for defeating the static heuristic detection, we published some obfuscator that does that. And to defeat the signatures, this is the subject of this talk. So stay with me. And to detect the emulator, that's one way to defeat it. And as with regards to real-time monitoring, you can just patch the different hooks, even if they are in kernel land, there is no problem to do that, and it will make the antivirus blind. So this is the way my talk is organized for the rest of the talk. The first thing that we have to do is to automate scans, because yes, maybe you run a red team and you have a set of tools that you are using for years now, and you don't want to change, but you want to be aware when a set of tools gets detected by some antivirus. And more specific to this talk, we want to apply thousands of mutations on a sample until the sample comes out clean. And to do that, we have to automate scans, and obviously we won't do that manually. And at this point, you might wonder why are we not doing it with VirusTotal? It's because for first, they share the sample with vendors. And the second one is the API is very, very costly, even for a company. Luckily for us, we have Tavis Ormandy on this earth, and sometimes he decided to create magical things, like the time when he decided to port Windows Dynamic Link libraries to Linux. And for us, that's a good thing, because Windows Defender scan engine is mpclient.dll, and it's standalone. And Load Library, the project from Tavis Ormandy, is able to run it. So it's perfect for automation. The problem arises with other antivirus engines, because sometimes they don't offer a command line interface, and sometimes they only run on Windows. To tackle that issue, I've decided to use VMware's VMrun. This is a tool that ships by default with VMware. On the right, you can see a command that you can run on a virtual machine, provided that you have the VMX file. And on the left, you see the mandatory parameters that you have to provide in order for the command to work. Obviously, that's the password and username of the guest operating system. More precisely, here are two commands that will be useful to us. If we want to automate a scan with VMware, we first have to copy a file from the host to the guest machine, and then we want to invoke the antivirus scan engine. And this is a more complete example with Kaspersky Antivirus. So here we call the VMrun command. We provide the username and password, call the run program in Guest, and we provide the path to the VMX file where I installed Kaspersky, trial version. It's enough. Then VMrun expects the full path to the executable to be run. In the case of Kaspersky Antivirus, it's avp.exe, which also expects the keyword scan and a file to scan. When your antivirus does not offer a command line interface, you can still rely on some oracle to know if the antivirus detected as malware or not. And to do that, I have two steps. First, we copy the file from the host to the guest, like usual. And next, we can leverage the fact that some antivirus will trigger a scan once the file is written to disk. And when that's the case, we can assume that the file will be deleted or put into quarantine. If the antivirus does not do that, most likely it will trigger the scan when the file is executed. So to do that, we actually run the sample, and later on we check that the file exists on disk. If it does not, it was not a malware, it was not detected as malware. If it's not there anymore, it was detected as malware. Now that we can automate scan, we will be talking about search algorithm in order to find signatures. So this is a common problem. We have a needle and we have a huge haystack. How do we find the needle in the haystack? Here in this case, I've chosen as example Mimikatz. Mimikatz is a 1 megabyte binary, and obviously not the entire file is detected as malware. It's only some specific parts in it that are detected, and we want to find them. This is a problem that has been with us for some years now, so obviously we have some public projects about it. The first I'm aware of is dsplit, which came out in 2006. The idea behind dsplit is to split a file into smaller parts and to see which small parts triggers the antivirus. And the further check, which came out in 2019, also does that, but in a better way. The problem with this methodology is that when you split executable files into chunks, you assume that the antivirus might treat the chunks the same way as it might treat an entire executable file. That's because of the portable executable structure. If you break it, the antivirus has no way to know that it's an actual executable, so he might skip scanning it. And the second reason is granularity, but more on that later. The solution for us was to still do mutations, but that are aware of the PA format. If you don't remember about the PA format, here is a quick reminder. It's a file format, so obviously there are a lot of headers that we don't care about. As a software developer, all we want to know is that your code will most likely be present in a text section, and the data sections contains initialized data that can still be written to. So most likely you will find your global variables here, and in the R data section, it's sections where initialized data are present, but they cannot be written to. So most likely you will find constants such as strings, and the other sections are less interesting. So if you were a lazy engineer and you were working for an antivirus company, what would you do to solve the problem of a virus like McAfee pretended to do? Most likely you will search for strings because they carry a lot of intent. Some developers even leave the double symbol path of their executable, and you can know the name of the person that wrote malwares. So it's a shortcut. Why not take it? But if you were to take that shortcut, where would you search for sequences of bytes? This is the same view as before, but laid out differently. If you want to find hashes or inline constant, you would look for them inside the text section. If you want to find shellcodes or other stuff, maybe take your chances with the data section. If you want to look for strings, that will be the air data section. At this point, you might wonder, yeah, sure, if I was a lazy engineer, I would do that, but actual engineers working in antivirus company, they won't do that, right? And I'm not saying they do that. I can only show you something, and you will make your own deduction. So here we have some files I have selected for the demo. Here we have a component of Meterpreter, and that's an option to trigger an antivirus scan. And here, Meterpreter detected as malware. Now, let's say I want to check my assumptions, and let's say I want to hide one section, which is the data section. This allows me to patch the file. And now if I scan it again, shit. It's not detected anymore. And it doesn't make sense because the data sections only contain initialized data. I would assume by the year 2022 that $1 billion companies would actually, run semantical analysis on files, and that's not the case. I forgot that slide. I've shown you metserver.x64.dll, And where does it come from? If you install Metasploit framework, there is a sub repo called Metasploit payloads, and you can fetch the latest versions this way. And once you impact the Ruby gem, you will find the following files that are scanned. Sorry. So we are lazy engineers, always, everywhere. So they target sequences of bytes of arbitrary length. And I also know by experience that strings or sequences of bytes have malicious or benign scores. And I don't care about benign scores, and I don't care about low malicious score. I want to find the fewest amount of strings that have the highest score. Why? Because let's say I have my results and I know which string are detected by Windows Defender or some other antivirus. I will need to patch them, and it's easier to patch 3 strings than thousands of strings. So I decided to rely on the divide and conquer algorithm. If you don't remember how it works, you have your haystack and it's too big to find your needle. So what you will gonna do, you will cut the haystack into halves, give one half to a colleague, and you will concentrate your effort on your own half, and it's still too big, so cut it in half, and so on, until you have a half small enough that you may just know if your needle is present in it. Of course, there are other ways to find stuff. I've also tried linear search, but it was not very efficient for me. More precisely, applied to executables and antivirus software, you want to split the sample, fill one half with random junk, and redo an antivirus scan. And then two things can happen. Either the file is detected as malware, either it's not. If the file is detected as malware, it means that the half you filled with random junk was not relevant for the antivirus. But the file that was left intact sufficed to trigger the antivirus detections, so you will concentrate your efforts on that. And you repeat that process by splitting the half that was left intact, and one half with junk data, one half left intact, and you repeat that process. But we can do better than splitting and scanning things. We've seen before the PA format sections, and there are different stuff in different sections. If the antivirus triggers on the text section, you know that in it you will find functions, so the granularity in there will be functions that you can recover with your favorite disassembler. If the data section is detected, most likely it will be a global variable. So I had no tools to do that, so build my own. And to react to a detections inside the air data section, we know there is strings in here. And it's a chance for us because Radar 2 works very well with strings, and we can enumerate them and have a granularity on strings. And talking about strings, here is a practical example with some Mimikatz. Mimikatz contains 5,000 strings, so it's way too much to do the analysis manually. And the strings have between 5 and 100 characters, so we have a good granularity. And applied to that, a divide and conquer algorithm would mean that we split the 5K strings into 2 clusters. For the cluster 1, we replace the content of every string in this cluster with random data, and we want to keep it the same size because otherwise we would corrupt stuff, and here we are precise. And the strings in cluster 2 are left intact. We patch the sample with this modification, and then we do an antivirus scan, and then 2 things can happen, as you understood well, and our reaction to that will depend on the fact if the malware is still detected or not. We repeat the process until we have 2 clusters that only contain 1 string in each, so that once we do the antivirus scan, we know which string was detected, and recursively we can enumerate all the strings that are detected. So I can do a quick demo, but I would prefer to to show you something I've already run, because I don't know if I'm not short on time, but it takes 3 minutes to run completely. So here is Mimikatz soon. The output is very verbose, don't worry. So we have our tool and we have Mimikatz. We just run the tool on Mimikatz and it will by itself figure out what are the things that are detected by Defender in this case. And to begin the analysis, the tool first patch every string. Let me jump to the end. And at some point, he did the divide and conquer algorithm, and he found that string first. That was the highest score string. And you may recognize it if you already used Mimikatz. It's the famous header, you know, à la vie à l'amour. And to me, I don't know about you, but it's very stupid to me that an antivirus would look for that. But yeah, anyways. And the other strings that are detected are the following. These are a function name, like real function name that are offered by Microsoft for you to use. They are telling me that the text was too small. So we found strings that once you patch them, the file is no longer detected as Mimikatz. But at this point, you might wonder, is that really true? Where's really the strings that are looked for by Defender? And I don't want you to take my word for it. And to prove that it's correct, there is only 2 ways to do that. It's to work at Microsoft and have Windows Defender source code. And unfortunately, that's not the case for us. So we have to rely on reverse engineering. And a guy named Komial already did the work. And a very esteemed colleague of mine, Romain Melchior, built upon that and fully automated the process. And what you are seeing here is the result spit out by his tool. On the top, you see the signature name. And in the middle, you see the raw binary data that are looked for by Windows Defender. And on the bottom, you see the strings that were extracted from this raw binary data. And you see the same strings that our tool found, like the URL to the blog of Jean Ticoui and the function names. Now, let's say that there is a signature in the data section. We know that there is most likely global variables in there. And it's hard for the human eye to recognize raw binary data. So what I did was trying to recover them by leveraging the fact that if you have a global variable, most likely you use it somewhere in your program. So you expect to find a cross-reference coming from the text section going into the data section. And that allows me to find the address of the global variables, which is not enough. You also need to know their length. And to do that, I made the assumption that the length is equal or less to the address of the next cross-reference. And then you do the divide and conquer algorithm on that. And you will be able to find the signatures that are detected by Windows Defender inside the data section. So let me get back to a demo. This time I will make the text bigger. Should be enough. Or not. This time it's good. So that's the output I've shown you before beginning the talk. And that was a component of Meterpreter. And the tool identified that the following sequences of bytes is responsible for Windows Defender detection. And if you patch these bytes, it's no longer detected. So what the heck are those bytes? And to answer that, I'm just going to grep like a Windows Defender does. These are the first 2 bytes that you are seeing here. And it spit out only 1 file. Good. And here you're starting to see interesting stuff, strings. But those strings are special in the sense that they are shellcodes. Not here. Here, that's the shellcode that is detected by Windows Defender. And yeah, it might make sense because this shellcode allows to transfer your Meterpreter session into another process. So you would infect another process with your Meterpreter session. But still, there are a lot of interesting stuff in the file that we've just seen, and Defender only is able to detect the strings in it. And here I've decided to show you some code, but don't worry, the goal is not to explain each line. I just wanted to show you how easy it is to, once you rely on powerful frameworks such as Radar 2, you are able to do stuff like global variable recovery. And the most interesting stuff is on the right. Pipe.cmdj allows to run a Radar 2 command and get back the result as JSON. And the subcommand axg allows to enumerate cross-reference and get back the result as JSON. And what goes on this function is exactly as I've told you before. But you might wonder, is that really necessary? And I've just shown you that yes, it's necessary to do that because some antivirus are stupid and will look for global variables. When all else fails and there is a section where raw binary data is looked for, you have to rely on chunks, and we know that's an issue because chunks may overlap, envelope, or intersect. And here I've chosen a special case, which really happened by experiments. Let's say you have an interval for a signature. You know it's somewhere in the middle of the file, but once you start splitting things, you will break the actual signatures, and the analysis won't be able to continue. To solve that issue, I relied on the interval trees because they are exactly made for that. You have to maintain a list of intervals. Once you have found a given interval, doesn't matter if the interval is very big, you remember it. And as the analysis goes on, you have smaller and smaller intervals. And once the analysis is finished, you can do queries on the tree of intervals, like which interval envelopes which other interval. This allows to filter results. And as a bonus, let's say that we have identified the strings that are looked for by antivirus engines. And you are lazy and you don't want to go into source code, patch the source code, and rebuild the software. You want to automatically patch the binary. But obviously, you don't want to break the binary. And if you just simply remove the strings, the binary might not work anymore. So is that possible? Is that possible to encrypt strings directly inside binaries? I didn't know at the time, but I took on the challenge, and this is the idea I came up with. First thing first, you need a decryption function that you want to inject inside the binary, because the binary was never meant to decrypt stuff, maybe. And then you encrypt every string, and for each string, you want to make sure that once the binary actually executes and might need the strings in clear text, you want to make sure that the strings actually is in clear text, so you decrypt it beforehand. To do that, you enumerate the cross-reference to each string. And for the first cross-reference, you hijack execution flow by patching some bytes. You redirect this execution flow within a switch table. And you take care of the registers. You save the original instruction pointer. And you set the correct registers to call the decryption functions. And once that's done, you can go back to normal. And here, some code again. I just wanted to show you how easy it is to hook stuff with radar2. Once you know a cross-reference to a given string, you can use radar2 to recover the assembly instructions that actually use the strings. And you have to overwrite those bytes with something that is small enough that is able to hijack execution flow, but not too big because it would mess up the assembly code. Then you compute the offset to the switch table, which will depend for each string. And then we assemble code with Keystone, and we inject the entire result with radar2 and the WX command. The hook content is as follows. You have to save the registers, obviously, and you want to call the decryption function. And then you want to do the, we overwrote some assembly instructions, so we have to put them here. And then we can resume execution flow. Next, we said that we need a decryption function. And I'm also a lazy person, so I didn't want to write my decryption functions in assembly, so I wrote it in C. And I built the binary with pi so that the function is fully position and independent. And then we can strip out the functions with Leaf. Leaf is a framework that is able to manipulate the executable file. And here I just wanted to show you again how easy it is to do that. Because Leaf offers functions called getContent from virtual address, which expects an address and a size. And both of which can be recovered with other radar2 and the AFLJ command, which allows to enumerate functions and there some things about the functions. And once you have the code of the decryption function, you have to actually inject it inside the binary. And in three lines of code, you can create a section and put some code in it, and that's done. Obviously, there are some limitations about the tools that we did. It's not for script kiddies in the sense that every time you use it, you will most likely need to patch something in it. And that's no issue for me because I use it some time to time, only when my binaries are detected. And for me, it's more of a library of features than a tool that just does magic and that we don't understand. And there are some things we might want to optimize, like the text sections. I did not bother to exploit the function boundaries, so I just searched for chunks because I did not meet an antivirus that was trouble enough for this task. And we could also analyze strings present in source code only, because when you are building a binary, you will find there are several thousands of strings that are not really used by your program, but they are in the binary because of the dependencies. And I highly doubt that Windows Defender will trigger on those strings. So you could save time and enumerate the strings that you have inside the source code of Mimikatz, for instance, and only run the analysis on that. You could also provide a makefile for a project that you want to build, and only build a subset of this program. And at first, it won't be detected by the antivirus, but as long when you add code, there is a point where the actual signatures will be inserted, and at this time it will be detected by the antivirus. And that will be your telltale sign that you have found your signature. And to conclude, this is a tweet that I saw from Tavis Formandi. To give you some context, MP Engine is the Windows Defender scan engine. And I found it quite amusing that he has to fix bugs that we report, and he has no idea why we are using his tool. So that's it.
Thank you, Vladimir. Is there any question? Yes. Here.
Did you check the tools by Quarks Lab called IRMA that do basically same as offline scanning for antivirus?
Yes, I did. I even tried to use it. As I understand, the free versions only comes with support for Linux versions of antivirus. And yeah, it was not suitable for my use case. I was looking for something much simpler. But I'm positive that it will work as well.
The free version is you can use Windows antivirus as well, but you need some licenses, for example, for Kaspersky or antivirus like that.
Yeah, I'm sure it will work very well. But load the libraries, it works very, very well, and it's installed in 2 minutes. So you can do however you want, and that's just the way I chose to go about it.
So I'm wondering if this ever happens on the divide and conquer algorithm specifically. Does it ever happen that none of the chunks are detected, but not necessarily because the detection is split into two, but maybe because the antivirus was using something in the chunk that does not contain the signature to maybe validate the file? So maybe like for an example, maybe it sees that some chunk has been replaced with random data and maybe marks the file as damaged and then no longer gives a detection because of that. Does that ever happen? And if so, are there like any ways to address that? I don't know if I explained that properly.
Yeah, I see what you mean. And the only times it happened to me was when I was overwriting specific stuff. And if you're very precise in your analysis and you overwrite, for instance, the strings and you respect the size, you won't break anything. But yeah, I see what you mean, and it's very important to not break stuff and be critical about the results you get back from the tool that we propose.
That makes sense.
If a signature is detected as signatures, of course you have to check manually inside source code and see if it makes sense. Because maybe, like you say, you have broken the file and the antivirus was emulating it, and since the file no longer can be emulated, the antivirus no longer decided to scan it until the end.
Thank you very much.
Other questions? If no, we can thanks Vladimir for the presentation.
Thank you.